time will come into play. Time will not be a thing defined perfectly mathematically, but will be a very useful mechanism to think about probability. Right? So we'll have to get into that question. How do we think in terms of probabilities about time? So let's start from the top. What is random? Why are things happening random? Like here's an idea that I had when I was a kid. We're saying if everything is controlled by the laws of physics, like all the atoms, all the molecules, all the sun movement, and that generates wind and water and whatever else it is, nothing will ever be random, right? If our brains are connected with, are determined by reactions and electrical signals and whatever else we have, nothing will happen at random. It may appear random, but it's not really random. So what is random? Is the snow yesterday, last night, was it random? Was it determined by some factor? Could it? Maybe I could not have predicted this rain last night a week ago or 2 weeks ago, but maybe somebody else, smarter, with much better weather measurements and tools and knowledge about the world, could have predicted the snow last night a year ago, right? They looked at all these things that maybe there's some aliens somewhere far away that they know so much more about the world than they don't have this sense of randomness that we have. Not to mention, if you're a religious person, everything is predetermined in advance by God, right? I'm not saying religion is good or bad. I'm saying religious people might think everything is already decided in advance for you by some divine power. If you are not religious, maybe you don't think that way. So what is random? There's no good and bad answer here. It's a philosophical conversation. Why things are random? He's laughing at me. Have you asked yourself this question? What causes things to be random? Yes.
Our lack of perfect knowledge.
Our lack of knowledge. That's good. That's a good answer. So your answer implies these things are not really random. Maybe, but we don't know them. They may be that this rain last night was determined long time ago, but we didn't know that, right? So we lack knowledge. What else is random?
Well, it's like go off of what you just said, like when you flip a coin, it lands on a certain way for a reason. It's not really random. You just don't know every air particle that it hits, how hard you threw it,
what finger you use to flip it, so on and so forth. We lack control. What else is random? What things can happen? Can your grade at the end of the term be random? You think it's going to be random? You don't think it's determined by, what you do and what I think and so on and so forth. You think I'm going to flip a coin and say, hey, you get a C, So, any other idea for what is random? I'd say the grades are likely to not be random. There's a little bit of randomness involved, perhaps, but that's not what random is. Anybody else? What's random? How about the fact that I draw a card from a deck of cards, or I don't know, I look outside and I see the rain, right? And I've observed that, but you didn't. So you didn't look outside through the window. I did, and I see the snow. Is the snow versus not snow random for me? No, why? Because I've seen it. I look outside the window and I see the snow. But how about for him who didn't look outside the window? So what I'm saying is I may have observed something that for me is not random, because I have the observation. But for another person that did not make that observation or that has no access to it, it may be a random thing, whether it knows or not.
So it's going to be that we lack perspective.
Right. In the sense of observation.
But doesn't that mean we just lack the knowledge that we get from the observation?
Right, but I also, there's another thing in here that I skip. The difference between knowledge and perspective may have to do with, is it something that already happened, whether it's something that will happen. So in terms of whether it's gonna snow next week, it's not a matter of perspective that much. It's not a matter of observation. It may be that a meteorologist knows much better if it's gonna snow next week. But in terms of observation, nobody have observed the snow that's coming next week. So, but knowledge may help in that sense. Understanding how to look at what's going to happen next week may be a matter of knowledge. Observation is for things that have happened already, but I've observed it and somebody else did not. There was a question in there, in the back? I see your hand up.
I mean, I was gonna say like you don't know what the outcome is. Like randomness, like is something that happens, but you don't know what the outcome is.
Right, so I think it's this last point here. Did it happen already? Right? We're talking about something that has happened and we can observe the outcome or not observe the outcome, or we're talking hypothetically about something that will happen or we are about to do and we didn't do it yet, but we contemplate what would happen if I roll a die or draw a card or flip a coin, right? Okay. So I leave it at that and we can elaborate more. You have another comment?
Yeah, I was just gonna say, like, what makes coin flipping random is that it's really sensitive to what you start with. Like, it's sensitive to your initial.
Right, so there's something that we know, like a prior or premise, right? And then there is some conditions that may favor some outcome versus other outcomes, but we don't control them. I think that comes down to control. And because we don't control them, things may happen in certain ways or not in those ways, right? How about this other question of difference between counting and probability? Is the probability just another way of counting? Maybe I should get to that once I show you an example. In many cases, it is. In many cases, it's going to come down to count certain possibilities, and it's going to be identical with what we've done on counting. Those combinations, permutations, so on and so forth. But you have to make a distinction between when I'm counting something, say, with sum rule or product rule, and when I'm talking about probability in the sense of time. So let me show you one example. I have here the first example, fair 6-face die. So the faces are 1, 2, 3, 4, 5, 6. Everybody's familiar with the die, right? One roll. So this, I'm going to call this S from space. Space of possibilities. And a possibility is one of the spaces. So the outcome, let me say here, outcome, so roll. Outcome is the face observed. On a die is the face that's come up. Right? This has many names: outcome, possibility, observation, sample. It depends a little bit on perspective, but often when we do an experiment, that's the experiment. We say, what did we observe at the end of the experiment? We roll a die, we see a face, we see the number on the face, right? This is one of the 1, 2, 3, 4, 5, 6. So I have the space here. I have an outcome, and I have an event. Is something I care about. So my event might be the outcome is at least 4, say 5. So how do I look at this? Here's my space. The possibilities are 1, 2, 3, 4, 5, and 6. So this is the outcome or possibility. And this in here is my event. Let's call this E1. Outcomes bigger than 5. And I could have another event. Here's another event. This is event E2. Outcome is even. Like 2, 4, and 6. Those are the even events. So we have 3 notions here. The space of possibilities, which is a set of what might happen if I do my experiment, right? What's going to happen, one of the 6 phases is going to come out. The outcome, which is the phase that comes out to that experiment. And then events are some property or attribute that characterizes a set. What are the events that I care about? This is saying I want a high outcome, 5 or 6. This is saying I want the even outcome, so on and so forth. So now, typically, if we don't specify anything, so that would be a rare thing, but in general, we want those outcomes to have the notion of uniform probability, or let me say uniform likelihood. That is, when I define a set of possible outcomes, again, unless I specify something about them, I meant every one of them has the same chance to come up. So I need another notion here, uniform likelihood. I can say same chance. This is another notion that we need to describe a little bit. What does it mean? When I say I have a die, this is also embedded here. This fair is the same as uniform likelihood when I say a fair die or a fair coin. How do we describe this mathematically? This thing that says, okay, you have a die. When you roll the die, the likelihood, which we're going to call probability or chance to see a particular face, is the same as the chance to see another particular face. Like the chances of seeing a 2 is the same as chances of seeing a 5. Notice that this is not a trivial thing. Some people modify the die, right? Some people put a little bit of metal on one side to make the other side more likely to show up. Some people modify the coins, so when you flip a coin, it's not a 50-50 whether you get a head or a tail. So not all things are uniform. But when you set up a probability, simple probability experiment, the space, it's nice if it's uniform. That's what allows counting. Right? So we have this notion here, or chance of likelihood. How can we define that or describe that before we get to the math? How do we say this die is uniform or fair? Every phase has the same chance of showing up. I'm dancing around this word, chance, likelihood, probability, whatever you want to call it. Is there a way to define this without using the word? How do I express this without, because I'm running in a circle here, right? I'm saying, okay, the chance is the same as likelihood, the same as probability, but I haven't defined any one of those things yet. So what do I mean when I say this die is fair or this coin is fair? Yes?
The average ratio of the occurrence of the event to the total number of times you've like performed.
So I need to go to this question here. To define this is just like he says. To define the chance or probability or likelihood, I need to refer to something called time. Doesn't have to be the time that Einstein was preoccupied with, how the universe started. It's a different time, right? So we need what is chance or likelihood? You say it's a ratio, right? Say we're going to define this as probability of some particular outcome. Ratio of count the outcome versus count the trials in time. This ratio has to be what? That's the chance. And if we want this to be uniform, how do we say uniform? So this it's an intuitive, we still not formal mathematics. Is if I roll the die 1,000 times, I'm counting how many times I've seen a 2, right? So let's write as an example here. If I roll the die n equal 1,000 times, and I observe outcome W equals, say, phase 2 100 times, then this ratio that I'm talking about is going to be 100 divided by 1,000. I observe the outcome that I'm looking for 100 times, and I roll the die 1,000 times. Now, for this to be uniform, the property I describe here, I want the outcomes to have the same chance, or to be a fair die. What this ratio has to be? Yes.
Each outcome must have the same ratio.
Right. So that has to be uniform, meaning roughly 1 over the size of the sample space. Right. If the sample space are 6 sinks, each one of them has to be 1 over 6. All right? So how do I measure these events now? I go back to the event notion, and I say, what is the probability of an event, say E1. Sometimes I'm just going to call probability of E1. And sometimes I'm going to use round brackets. Different books use different things. How do I look at an event? Now, an event is not an outcome. An event is all outcomes that have a certain property, right? Like my event here, event E1, 5, 6, clearly has 2 outcomes. It's the 5 and the 6. So we have now 4 notions that we're talking about. One is the sample space. What are all the possibilities when I roll the die? That's yes. It's the set of 1, 2, 3, 4, 5, 6. I have individual outcomes. Those are what can happen if I roll this die. It's one of those 6. Those are my possibilities. I have an event that says some of these outcomes are the ones that matter to you. Event E1 says it's those 2. Event 2 says it's those 3. And we have this notion of chance or ratio that says for each particular outcome, if I do this repeatedly many, many times, how many times I'm going to see that outcome? And we call that uniform, where all outcomes have kind of the same ratio. So in here, we're going to call this probability. This is the probability of this outcome. And we have our first rule here. If I look at all possible outcomes, all these 1, 2, 3, 4, 5, 6, what happens when I add their probabilities? I get 1, right? That's the idea that one of them must happen. One must happen. And only one can happen. Outcomes are completely disjoint. If I roll the die and I see a 5 in the same roll, I can't possibly see a 3. It's one of those things that happen. So I know it sounds trivial when somebody explains it on the board, but students have difficulties describing the space here. Like somebody gives you a problem, there's candies over a few days distributed to a few people, and some candies gets on the floor, and some candies get picked up, and some candies get traded. What is the space? Take a moment and ask yourself, what am I really experimenting with? What is my experiment or run? And what's the outcome of that run? It's not always as easy as here's 6 possibilities. The space of possibilities are those 6 and nothing else. So I have this relation here of the outcomes. And now, if I want to do probability of an event, how do I do that? Probability of an event is not the same as the probability of an outcome, because an event can have multiple outcomes that are checking out that event. So what is this going to be? This is going to be the sum over the outcomes that are part of that event of the probability of those outcomes. So for event E1, this is going to be who? The probability of seeing a 5 plus the probability of seeing a 6. How many people follow me so far? Hands up so I can see them, please. Okay. So what am I saying? Am I saying that I have a certain probability of seeing a 5 and a certain probability of seeing a 6, and those are uniform. So if they are uniform or fair die, then how much is the probability of 5, which is the same as the probability of 6? That will be what? 1 over 6. So in that case, the probability of the event E1 seeing a 5 or a 6 will be what? 1, 6 plus 1, 6, that will be 2, 6, or 1, 3. And we can make that 0.33, right? If we want to transform it into a decimal number. How about the probability of event E2? If it's uniform, is the probability of 2 plus the probability of 3 plus the probability of, sorry, not 3, 4, plus the probability of 6. This will be 1, 6 plus 1, 6 plus 1, 6 equal 1/2. So in a uniform space, it's easy to visualize this, right? In a uniform space, I say how many things are here? Are 6. Event E2, how many of those things are in the event E2? They're 3 out of 6. So if the space is uniform, 3 out of 6 will be roughly a half. But if it's not uniform, if my die has been modified and it's not fair, it's not like all events, all outcomes have the same probability, then 2, 4, and 6, that's still the probability of 2 plus the probability of 4 plus the probability of 6. But it won't sum to 1/2 anymore. All right? So what about the event? Let me see, I have another one here. Here's event E3. Outcomes. I want to modify the space first. So now I roll 2 dice. Or I roll the die 2 times. So what's my space if I roll this die 2 times? What is the possibilities if I roll a die once and again? What am I going to get? It's not 1, 2, 3, 4, 5, 6 anymore, right?
2 through 12.
How many?
2 through 12. So.
Well, but I'm not summing up.
Oh, okay.
Yes,
so
right.
it'd be set of 1, 1, set of 1.
So that'd be, I can get a 1, 1, 1, 2, up to 1, 6, and then a 2, 1, 2, 2, up to 2, 6, and then 6, 1, 6, 2, up to 6, 6. That's the same as saying this is the set 1, 2, 3, 4, 5, 6 times the set 1, 2, 3, 4, 5, 6, right? Cartesian product. How many things are in here?
36.
So now I want to define an event. I don't know where it is. The sum of the 2 rolls is 7. What are the outcomes? So this a W, an outcome is one of these pairs, right? The space, it's all those pairs. When I roll the die, I can get one of those. There's 36 outcomes. Are they all equally likely? If my die was fair, meaning the first time when I roll the die, everything can get 1, 2, 3, 4, 5, 6, equal probability. When I do the second roll, I get all these possible pairs. Are all of them equally likely? So can I say for any outcome in S, right, this W is a pair, the probability of that W is 1 over 36? Right. We need a little bit more theory to do that. We'll get to it on Tuesday. Why is that happening? It has to do with the fact that the 2 rolls of the die are independent of each other. It's the same as rolling 2 dice in the same time, which they have no connection to one another, right? In many fun stories about casinos and how people cheated and so on and so forth have to do with this independence notion. The way people can predict in, I don't know, a blackjack or some other things that some combination will be more likely than other. There were movies made about this. I remember a movie, I don't know the name, with Kevin Spacey that some MIT students went to the casino and they managed to beat the casino. All those things, which are true stories, refer to the breaking the independence. Once I see something happening in a deck of cards on a roll of die, I may be able to say the next roll of die or the next card is not equally likely due to the way the cards get shuffled, due to the way the cards get arranged, due to the way the people sort their cards in hands, whatever. Sometimes it's not independent, and if I know how to manipulate those probabilities, I can get an advantage in your casino. Back to this, what are the events, the outcomes that sum to 7? 1, 6, 2, 5,
3, 4,
3, 4, 4, 3,
5, 2.
5, 2. So how many are here? 6. And so the probability of this event is 6 times 1 over 36. That is 1 over 6. So what is the probability to get, yes?
But can't you also do the other way? It's like order math is right. So can't you also do 6, 1?
Yeah, it's in here, right?
Okay.
6, 1. So I got 1, 6, and 6, 1, so on and so forth. Some more examples. So that's with a die. How about another event? I'm still in this two-die roll. Event E2, the total, that's the sum of the two rolls. Is at least 8. So I want, is this the same as asking, so I want all the pairs that sum to 8 or more, and I'm saying I can formulate this as a counting question. I'm gonna say, how many pairs have ij, have I plus j at least 8, divide that by 36. This question of event has more than 8 comes down to counting how many of these pairs have the 2 at least 8. And then, so how do I do this? I could enumerate them, I could go through them and count them. Is there a way to not do so?
Since you have the matrix inside your set right there, you could find the first point on the side to the right, so 2, 6, and then 6, 2, and draw a diagonal line between them, and any one to the right of that line.
1, 2, 3, 4, 5, 6, like that. So this is 1, 2, 3, 4, 5, 6. I think
Yeah.
you mean to count, to put this here, the sums.
Yeah.
2, 3, 4, 5, 6, 7, 3, 4, 5, 6, 7, 8, 4, 5, 6, 7, 8, 9, 4 plus 1, 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, and 7, 8, 9, 10, 11, 12. So you mean this diagonal?
Yeah.
So what he's saying is, you look for these 8s, and everything on this side of the diagonal is the numbers you're looking for. So can we count those? This is how many things we have on this one. We have 1 here, 2 here, 3 here, 4 here, and 5 here.
Yeah.
So how much is that? 1 plus 2 plus 3 plus 4 plus 5. So that's 15 divided by 36. All this counting works if same if uniform. This idea of count the possibilities and divide by how many they are 36, works because every single pair has the same likelihood or probability to happen. If that wouldn't be true, then this wouldn't work that way. All right. How about a different example? I have a deck of cards there are 4 suits. Everybody knows the suits? Clubs,
Hearts.
diamonds, hearts, and spades, like that. And each suit has 13 values, which are 2, 3, 4, 5, 6, 7, 8, 9, 10. Then
Jack, king,
Jack.
queen.
I'm going to say here Jack for people not familiar with this is the queen. This is the king and the ace. So typically when you play cards, these are in this order. 10 is more than a jack, jack is more than queen, queen is more than king, king is more than ace. But not every single probability implies this order. So how many total cards we have? 4 times 13, 52 cards. So here's my experiment or trial. It says here, draw 1 card. At random. When I say this draw 1 card at random, what is the probability for a particular card? Say, for example, the queen of diamonds. I think we should write diamonds, queen. What is the probability to get that card? If I say draw 1 from the deck at random, I mean uniformly random, right? So the chance of choosing that particular card is 1 over 52. You have to see how this goes to the uniformity. If we don't specify anything, it's very common sense that if I pick a random card, it's any one of the 52 cards is equally likely. But many problems will specify some sort of event or pre-event or condition that will make this distribution not uniform. And then I don't have the probability of 1 over 52 in that case. So my S space in here is exactly that. It's the clubs, 2, 3 up to ace, diamonds, 2, 3 up to ace, hearts, 2, 3 up to ace, and spades, 2, 3 up to ace. So this S is 52 possibilities. The W, or the outcome, is the card observed. And now the event, I want the card to have a face. Face means these guys have faces. If you're familiar with the deck of cards, those are the face. So that the value has to be at least jack. What is the probability of this event? Because it's uniform, because I'm drawing from a space where all the outcomes have the same probability, is the number of face cards divided the number of possibilities, all cards. So that is what? How many face cards are there? 16 divided by 52. This is the same as counting. This problem could be written as count the number of face cards, right? Because being uniform, I divide by how many cards I have. How about I say I draw another experiment. I draw 2 cards. And I'm asking what is the probability? So the event is they are in the same suit. So both of them are clubs or diamonds or heart or spades. How do I do this? So I draw 2 cards. My space is not that space anymore. My space here is what? Is it the same like in here where I had the space, the Cartesian product? In here when I did the space, I say, well, if you roll the die once, you get 1 to 6. You take that roll, you roll it again, you get another 1 to 6. So you have 6 possibilities times 6 possibilities, that's 36 possibilities. Is it the same what I'm doing here? I'm saying, here's a deck of cards. You draw at random 2 cards from it. Does it really, is it gonna really be 1 to 52 times 1 to 52? All possibilities times all possibilities? Yes or no? Why not?
You took it out and you just put it back.
Go what?
You took it out, but like it's not in there anymore. So there's
Right,
nothing
so
there.
that would be the same if I put the first card back. If I take a card, look at it, write it down, I've got the Queen of Diamonds, then put it back in the deck and draw another card, that would be the case. So that would be, it's called, somebody said it, with replacement. Means after each draw or each sample, the deck is the same. It's back to full. Or the card obtained has been put back into the deck. But that's not what this is. If I put the card back, that's what I'm going to get. But I'm not putting the card back, so this is without replacement. Take two cards at once. Or take one and take the second from remaining cards. So what is my space in here? It's not, this is not the space for this problem. This would be if I put the first card back. A space in here is what? What can happen if I take two cards from this deck without replacement? What's the outcome of this? Yes?
Will the quotation be 1 to 52 cross 1 to 51?
You mean the size?
The size.
Yeah, but I'm asking what's in the set. I think you're close, but not exact. So these are all the pairs of two different cards, right? That's my space. When I get two cards, I get all the possible pairs of two cards. So how many pairs are in that deck? The size of S is what? Back to counting. How many pairs are in a deck of 52 things? 52, choose 2, which is who? 52 times 51 divided by 2. Right? Now, my event is same suit. What are the pairs? How do I think of how many pairs, number of pairs of cards in same suit divided by, this is the probability of the event, divided by number of all pairs, right? I know the bottom one, that is 52, choose 2. How many pairs are in the same suit? If I look at all the pairs, all the possible 2 cards, how many of those pairs have the same spade and spade, clubs and clubs, diamonds and diamonds, hearts and hearts? Yes. 4 pairs?
5.
I could have any value, the jacks, queen, aces, 10, 5, 8s. I'm asking, in how many ways can I take pairs that are in the same suit? So before let's recap, maybe I'm going a little bit too fast here. I draw 2 cards from a deck, right? That's what I'm doing. The number of possibilities is 52, choose 2. Those are all possible different pairs that I can get from a deck. But some of these cards, some of these pairs will have the same suit, will be 2 clubs or 2 diamonds or 2 hearts, but different values, right? Could be the 10 of diamonds and the jack of diamonds. And some of these pairs will have different suits. Will be any club with any diamond, or any club with any heart, or any heart with any spade. So how many of those pairs have the same suit? Yes.
4 times 13 choose
4 times 13 choose 2. What's the thinking behind this thing? How did he get to 4 times 13 choose 2? Where is the 4 coming from?
4 suits.
4 suits. And where is the 13 choose 2 coming from?
Choosing 2.
In that suit, how many pairs are out of 13 cards? Because that suit has 13 cards. So how many pairs can be taken, right? What about if I want to count this as, so the bottom is still 52 choose 2, and I want to count the pairs in the same suit by taking the total 52 choose 2 and subtract the pairs that are in different suits. So you've seen this in counting. Sometimes when we count something, we say we can't count that, but we count the complement of it, the pairs that don't have that property, and we take it out the total. The total is 52 choose 2, right? That's all the pairs. So I'm asking, how many pairs are from different suits? Because if I take those from the total, I get the pairs in the same suit, right? How many pairs are in different suits? In how many ways can you make a pair that's, say, diamonds with hearts, or hearts with spades, or spades with clubs? We're back to counting. This is a good weekend for you guys to go back to n choose k and permutations and all that, because this is going to happen big time starting next week, right? A lot of this problem come down to counting. Yes?
52 times 39.
52 times?
39.
Okay. Where he came up with this?
You pick one card, and then the next one is anything that's not of that suit.
So this is, say, the first card can be any one of them. There's 52 possibilities there. And this is the second card, which he's saying could be any card other than the suit that I just picked. So how many options are for that second card?
51 minus 4.
Right, it's all the cards in the other 3 suits. So this, whatever suit that is, this would be that. But what about the order? Are we, I think we are off about the order. Did we include order here? When we say 52 choose 2, did we count the fact that the pair could be, if I think about the first card versus the second card, and the other way, I could same pair, unordered pair. Is this counting order here? I'm not sure at all.
It's not part of
I think there's a problem here. I have another one for you to see, to verify. How about if I say 52 choose 2 minus, I say pick 2 suits, 2 different suits. In how many ways can I pick 2 suits? I have 4 suits. In how many ways can I pick 2 of them? Like the diamonds and the spades.
4 choose 2.
4 choose 2. And now that I pick the 2 suits, how many pairs can I make with one from one suit and one from the other suit?
13 times 7.
What's the answer? So again, what did I do? I want to get all the pairs that are not from the same suit. So how do I do that? I choose 2 suits. I can do that in 4 choose 2 ways. And now that I have the suits, how many pairs can I make? I have 13 cards, 13 diamonds, and 13 spades. How many pairs are there?
13 squared for 3.
13 squared? Is that the same as that? Is the same as this? Because they gotta be the same, right? That's something for you to do. I'm gonna leave it at that because this is a counting problem now. But you can see how these problems in a uniform distribution, because in here all the pairs are equally likely, right? when I do the die rolls or the possibilities are equally likely. It pretty fast comes down to accounting problems, counting how many pairs have the property you want. So I think there's a problem with order here. This might be incorrect. Here's another one. I have an urn with 15 red balls and 10 blue balls. If my experiment is draw one at random, when I say this, what do I mean, what do I imply about the distribution? How the events are distributed. Of course, there is a sample of events, right? The sample of events will be what? What are the outcome when I draw a ball? Are those balls identical or they have IDs?
Identical.
Identical. Are the cards identical or they have IDs? They have IDs. So the outcomes, is it 25 outcomes in here? But how many outcomes are there? 2 outcomes. Are the 2 outcomes equally likely? No. So, okay, probability of red outcome is
2/3.
15 by 25, right? And probability of the blue is 10 by 25. So if I draw one at random, probability of red will be 15 by 25. What is uniform in here? The red and blue are not uniform. Clearly, they don't have the same chance of showing up. But what is uniform? Intuition. There is something uniform going on. Yes?
Each ball is equally likely.
Each ball, those identical balls that don't have IDs, when I put my hand into the bag, each one of the 25 balls, it's equally likely. This is an absolute fundamental understanding that you need to have of a problem. Even if the outcomes are non-uniform, what is the uniformity of this problem? There is some control of these chances or likelihoods. The control is usually implied by the uniformity of something, in this case the balls. Sometimes it's given. Sometimes they tell you there is a die, and the die has the following probabilities. The 6, it's much more likely than the other faces. The control is given there. But in here, there is no specific, explicit given control. The control comes from the fact that every ball, we assume, it's equally likely to be drawn up. What if I have another experiment? I draw 3 balls at once. When I say at once, I mean what? Without replacement. So what is the probability of 2 red and 1 blue? So when I say this, what are my outcomes in here? What's the space? When I draw 3 balls, what can happen? I can have 3 reds, 3 blues, 2 red, 1 blue, and 2 blue, 1 red. So what's the chance of 2 red, 1 blue? How do we transform this problem into a counting problem? At what level we transform it? I know the balls are identical, they don't have IDs, right? So you can't say we have so many outcomes. There's only, if we look at those identical balls, there's only 4 possible outcomes. These 4 outcomes are obviously not uniform, right? They don't have the same probability. So these are not the ones that we need to count on. To transform this problem into a counting problem, we need to count the way the balls come out, right, at the ball level, because that's what's uniform, right? So what is uniform? In this problem, now I draw 3 balls. In this problem, what was uniform? Every ball was equally likely, right? I draw 1 ball, every one of the, how many balls I have? 25 balls. Every one of these balls have the probability of 1 over 25. So in other words, if I say now balls have IDs, what would be my sample space if balls have IDs? Red 1, red 2, up to red 15, blue 1, blue 2, up to blue 10. How many of those are here? 25. Okay, is this a uniform space? Is it the case that each one of the balls have a same chance of coming up? This is uniform. This was not a uniform space. If you look at the outcomes red versus blue, they're not a way to count those, right? So I counted the uniform space, and the reason I came up with 15 by 25 is I'm counting what are the balls that are red. If I want to do the same here, I have balls have IDs. What are the outcomes when I draw 3 balls? That's how many, but what are the outcomes? This would be triplet of balls, right? Like 3 balls. So how many of those are here? How many triplets of balls if I have red 1, red 2 up to red 15, blue 1, blue 2 up to blue 10? It's written on each ball, blue 7. What are the triplets? I mean, how many triplets are in here? There's 25, choose 3, right? Because I have 25 balls, and any 3 of them out of order form a triplet. So how many triplets have 2 reds and 1 blue? How do you make triplets with 2 red and 1 blue? Yes. 15 choose 2 times 10 choose 1 divided by 25 choose 3. So where is this coming from? This is the pairs of 2 reds times any blue divided by number of triplets. What did I just do again? I want to transform this probability problem into a counting problem. But if I define, this is a valid set of outcomes, right? Because the balls are identical. If I define the outcomes that way, it's almost impossible to count, or at least I don't know how to do it. It seems easier to define the outcomes this way, give the balls IDs, and then do the counting at that level. Now, there's many ways to solve this problem. It's just the trick in here is not get lost. If you start with balls have IDs and you count how many ways can you get blues, then keep going with IDs and obtain the problem that way. In a uniform space, you have the advantage that you count the events you like, the ones with 2 red and 1 blue, divide by the total number of events, that's your probability. But to do this, the space have to be uniform. Each triplet of balls have to have the same chance. Otherwise, counting that way doesn't work. What else? What if I ask probability of 3 same color? What do I get? how do I get all that have, all triplets, all three balls have to have the same color? What's the number? Yes.
So you get 15 choose 3 plus 10 choose 3.
So that's all the three reds, triplets, and this is all the three blues, triplets, divided by how many triplets are there. All right. How about if I have this problem with replacement? So I have same 25 balls, 10 blues and 15 reds. I draw 3 balls, one at a time, and it's put back after draw. So the difference between this and the first case is every time I take a ball, I look at it, I know, I write down its color, but then I put it back into the bag before I do the next draw. That's why it's with replacement, because at every draw, the bag was the same as I started with. What's the probability of all red? I want to transform this into a counting problem. Just make sure it's a uniform space to do counting. Now with replacement, it's not like that. It's something else, right? What's the probability to take a ball, see if it's red, put it back, take another one, red again, put it back, take another one, red again? Somebody else, yes.
Would it just be 50 cubes over 25 cubes?
Correct. So the way this goes is the number of red triplets divided by all triplets. Now this is all with replacement. How about, can I say in terms of probability, can I say what's the probability of a red to start with? Times the probability of red again, times the probability of red again. I imagine this event is pick a ball, check if it's red. You're done, put the ball back, done. The next day, pick another ball, see if it's red, put it back, leave the bag alone. The next day, check a ball, see if it's red, put it back in the bag. Can I say it's that way? The probability of red is 15 divided by 25 to the cube. Why is it that I can do this kind of thinking? Somebody else. I can imagine this draw here of 3 balls as 3 separate draws and just take the probability of each one of them and multiply the probabilities. There is something that allows me to think about this way. What is it? Yes.
They're independent.
The three draws are independent of each other. So let me make a quick parenthesis in terms of how to study for probabilities right now if you don't know probabilities. If you know probabilities, you're probably safe to stick with what you know, because probabilities takes a while to settle in your mind. And if they're already settled and you feel comfortable and it makes sense what I'm saying here and you can do the exercises, it's not a good idea to unsettle what you have. Unless it's completely wrong, which I don't think it is. But many students don't have this quite settled, so what do? Let me give you a little trick. The book and the slides and the notes and Wikipedia make an attempt at defining independent and also defining things like sample. If I were you, I would ignore that for now. Again, if you're a mathematician and you later on get into math, you gotta know what sampling is, you gotta know what independent is. But for right now, it will be much better if you feel uncomfortable with probabilities, that is, to use the common sense definition of independent and sample, not the mathematical definition. Because that can get complicated and get you confused in a way that won't help your exam, quizzes, and so on and so forth. Only later, when you need real math, you may need to know exactly what independent is. For now, what's the common sense version of independence, not the mathematical version? What do I mean by independent of each other?
Each of them has no effect on the other.
More specifically, the probability of one of them would be the same whether it happens before or after the other. Right? So in order to think of this independence, say, there's two events. I'm going to get a nice Christmas present, and I'm going to get an A in this course. Christmas present from my parents, how about that? And an A in this course. Are those independent events? Are you going to get an A, a nice present, independent of whether you get an A or not in this course, do you think? If you get a D in this course, do you think your parents will I don't know, buy you a motorcycle?
Will they know by that?
I mean, that's different. Different people have different parents and different criteria of thinking about it. You see where I'm going with this? I would use the common sense notion of independence. Is my Christmas present going to depend on the grade in this class? In other words, if I ask Virgil, hey, can you please give me the grade in January? So that my parents buy me the motorcycle and then I come home with a grade. That means the events are independent or not? They are dependent because the motorcycle present depends on the grade in the course. How about independent events? What's independent? Yes.
Us coming to you and when our grades come out?
Are you coming to what?
Two independent events, or whether we come to you or not, and when the grades actually come out.
Right, whether you ask me or not, and when the grades come out, because that's up to John McCrary, right, the course coordinator. That's what he means. I know there is a formal independence formula in the book and in the slides, and if you already know probabilities, that's the one that you know. But this could get tricky in the sample spaces if you are not familiar. It's much more easier to think in terms of common sense English first. Do things depend on each other now? How about this classic problem that you see in all textbooks? I have a gauge on my dashboard in my car, and I have a fuel tank, and I have a sensor. And the light on my dashboard may come because the sensor's broken or because I'm out of gas. So I have three events. Sensor is broken, I'm out of gas or not out of gas, and the light comes on or off. So each event has two outcomes, right? Broken versus not broken, the sensor. The gas tank is full or empty or not empty, and the light on the dashboard comes or doesn't come. Which events are independent and which ones are dependent? I have three events. The sensor is working or not, the fuel tank is empty or not, the light comes out or not. Which events are dependent? Yes?
The sensor and the gas tank are independent, but the light coming on is dependent on both.
Right. The light coming on is dependent on both of them, but the sensor and the tank are independent events. It could be full or empty, the tank, and the sensor could be broken or working properly. They don't depend on each other. Right? The sensor doesn't break because the tank is empty. It breaks for other reasons. Here's an extreme version of this uniformity to make a little bit of a joke here. It's in the slides. Win the lottery, right? Needless to say, this is wrong. win the lottery, win, not win. Therefore, there's two options, right? Either win or not win. Probability of a win is 50%. Right? Because there's two outcomes, right? And 1/2 is 50%. You can see how obviously wrong this is. What's the problem here? This is not a uniform counting distribution of events. So what is uniform? If I go back to the lottery and say, wait a minute, I need a way to count things, but counting means I need something uniform. What should I count? Somebody else. So how do we compute these chances in lottery, right? If you ever play the lottery, you get a lottery ticket, has digits on it or 6 digits, and then somebody draws some digits, and then if your digits match, you win. Somebody else. What are we gonna count there? Yes.
You can count like the total number of lottery tickets and then how many you have.
And the total number of lottery tickets comes down to what mathematically? I mean, how many lottery tickets are there?
The different combinations of the numbers.
Different combination of the numbers. So it's how many different combination of 6 numbers there are, right? Versus how many combinations win in lottery. It's usually one or very few of them, right? Here's another one that I have. Strike by lightning. Right? Strike, not strike. So the probability of lightning strike is 50%. I'm making an exaggerate, it's in the slides, but what is the thing with lightning? This is not uniform. So if I wanna, now to the real point, if I wanna say, okay, what's the probability of lightning strike? How do I measure that? In the lottery, we said, we count, okay, the lottery sells 6-digit tickets. How many 6-digit tickets are there, right? And then we say out of the tickets, how many of those are drawn? Maybe they draw 3 or 4 winning tickets. That'd be those 4 divided by how many there are. How about lightning? How can I measure the chance of have a lightning strike on my house? Somebody else. Yes.
Number of strikes in general, and then you guys take the chance, the probability that, or the number of times that people actually get struck by it.
So the number of lightning strike we said in general?
Like just that come out of the sky.
Okay.
And then that's the denominator. The numerator would be how many times people actually got struck by those.
So he's saying, he's imagining, I think, some sort of version where here's all the surface of the planet, and here's all the strikes on it, right? So many strikes. And in some of those strikes are actually people being struck by lightning. Is that it? So it's saying these number of strikes are hitting people, and these other strikes are not hitting people. Therefore, the chance of a lightning strike is how many I have here divided by the total number of lightning strikes. Is that correct?
No.
Somebody else.
You have to take into account the odds of it hitting you as well, or out of all the people in the world, or all the people in the area where the lightning's happening.
So that's in here. If this is the area of the planet, right? Everywhere lightning strikes. This was a dude in I don't know, Chicago, Illinois, and then the lightning strike was on him. And this was another lightning strike in Siberia somewhere. Didn't hit anything. So what if I say, okay, so the chance of a lightning strike, suppose I have here, I don't know, 10,000 lightning strikes, and out of them it hit people, 3,000 people. Okay, not 3,000.
30.
30 people, fine. This is still incorrect. The number is not 30 by 10,000. The chance of a lightning strike is not 30 by 1,000. So what we all recognize here is that we don't have a theoretical way to measure lightning strikes. We don't measure it by physics of a lightning strike in theory. We measure by data observation. We go back 100 years and say how many people got hit so far by lightning strike, where they come, da 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 da. That's what machine learning and data mining do. They go back with the data and say, what have I observed? It's not a theoretical measurement, it's just counting the observations. So that's called empirical counting as opposed to theoretical counting. All these problems we did with deck of cards and dice and whatever else, right? Those are theoretical arguments. We didn't actually roll the die. We didn't go back to see how other people roll the die. We knew the die faces and we did a theoretical counting. And this is an empirical counting because we can't do a theoretical counting of lightning strikes. We don't understand enough physics to do that. But even so, there is a problem here with this calculation. If really there were 10,000 lights before and 30 of them hit people, the chance of a lightning strike to hit you is not, the chance to get hit by a lightning strike is not 30 by 1,000, by 10,000. Chance or probability to get hit by lightning. There is a premise going on here. For this to be the correct answer, this assumes a premise. What's the premise?
Lightning is fair.
There is a lightning strike. So this in here is the correct value if I say probability to get hit by lightning if there is lightning. So this number is what we call a conditional probability, save that for Tuesday, which is the probability of hit by lightning if there is a lightning strike. The reason that's not a correct in general, probability just to be hit by lightning, is because lightning itself is a rare event. Right? That's the problem here. In the premise that there is lightning, if I say, hey, there is lightning going on around because there's thunderstorms and all that, then in that premise, there's a chance to get hit by lightning. But overall, the chances of lightning are quite small.
Why do you not have to take into account the chances of like you being hit? Because are you talking about people in general or like a specific person getting hit?
Well, but it depends what the premise is. If the premise is there is lightning, we come back to this. We know there is lightning, so out of the lightning strikes, which one hit people? The one you're saying is if I say somebody got hit by lightning, so I know there is a person that got hit by lightning, what's the chance that that person is me or my friend or my neighbor? So you have to evaluate this as a count out of the premise count. In general, the chance to get hit by lightning is extremely small because lightning is a very rare event itself. So we need some other math here to do these formulas. This is a double event sort of thing. First, there's got to be lightning, and then if there's lightning, what's the chance that lightning is going to hit me? So we'll do that on Tuesday. Let's do some more examples. The key of all the lecture today is defining that space of outcomes properly so you can do counting. Counting comes down to the problems we studied 4 weeks ago. N choose K and permutations and all that. That's the counting. Once you have the space set up properly to do counting in. What if I say, draw two cards, what is probability of two aces at once? How many pairs of two aces are there? 4 choose 2 pairs of aces divided by 52 choose 2 pairs total. What if I have a poker hand? That's 5 cards. And I want full house. Full house is 3 same value and 2 same other value. Like for example, I can have 3 kings and 2 sevens. Right? That's a full house. So if I give you a random 5 cards hand, that's draw at once. All the card games, you cannot have repetitions because once you have a card, the king of clubs, you can have another king of clubs in your side. I mean, you can have another king of clubs in a different game with a different deck, but in that game, there's only one king of clubs. So in card games, it's without repetitions. If I have a 5 cards hand, what's the chance for that to be a full house? In other words, how many 5 cards hands have this property? 3 of some value and 2 some other value.
13 choose 3 times.
Hold on. 13?
Yeah, choose 3. And then 12 choose 2. Over 52 choose 5.
Is that true? Where he came up with this? What is 13 choose 3?
Three cards with the same suit.
Is that the same suit though?
I don't know. He said that. Don't blame me. I just wrote down what people said. What is 13 choose 3? Where is this coming from?
Cards of the same suit, not cards of the same value.
So this is 13. This will be 3 cards of same what? Suit. But that's not what we want, right? We want 3 cards of same value. So okay.
Just 4 choose 3.
That's a different problem. We don't say it's wrong. We say I answer a different question. What is it then?
13 times 4 choose 3 and then
Say again.
13 times 4 choose 3 times 12 times 4 choose 2
Times 4.
times 12 times 4 choose 2
Like that?
over 52 choose 5.
Let me say here different problem. So where is this coming from then? What is 13?
The number of different values that a card
This
can
is
have.
values. Values for triplet, right? Value for triplet. He's picking which value have 3 of the same kind. Now I pick a value, suppose that's a 8. What is this?
That's choosing like this when that the suits of that card.
Suits of the triplet.
Yeah.
There are 4 of them. I could have chosen this suit differently. I could have said which suit is missing, right?
Oh yeah.
Right. I could have said I have 4 suits. I need to choose 3 of them. Which one's missing? What is 12? The other value. This is the value of the double. And why is 12 and not 13? Why not? Why can't it be the same value?
There's only 4, not 5.
Yeah, there are only 4 cards of any one value. You can't pick 5 for value.
And also the definition of a full house says that the double has to be another value.
Right, that's if you know poker, but I don't know poker. So why is this value can't be the same value again? There are not that many cards of the same value. And this is the suits of the double. Again, this, once you get into here, it's exactly a counting problem, right? The denominator is how many outcomes are in that space. which in our space, the number of outcomes is how many different hands of 5 cards you can have from a deck. Once you do that, you're just back to a counting problem that says, here's how I'm counting all the full houses. But make sure you set it up correctly to get a uniform counting. I have some other examples here. I roll a die 3 times. So I get 3 rolls. Roll 1, roll 2, roll 3, or value 1, value 2, value 3. All pairs. And then I'm asking what's the probability that the sum is 17. So how many I have here? How many possible events I have in if I roll a die 3 times? 6 cube. And what are the events, what are the outcomes that sum to 17? Six, 6, 5. What else? 6, 5, 6, and so the chance is okay, here's another one. Probability that the rolls out of order are the set 1, 2, 3. I know this is very easy. 1, 2, 3. The sequence 1, 2, 3. 2, 1, 3. 3, 1, 2. So on and so forth. How many of those things are there? So I'm asking what are all the rolls that if I look at them out of order, I see a 1, a 2, and a 3. I'm trying to recap a little bit about how counting goes. How many rolls will be there that will have a 1, a 2, and a 3? Again, the rolls that I counted here are in order or out of order?
In order.
They're in order. So if I look at all orders that give me a 1, a 2, and a 3, how many orders are there? How much? 3 factorial. These are all the permutations of 1 and 2 and 3. So the answer is going to be 3 factorial divided by 6 cubed. Here's one more. Two more we're going to do. And then I have 7 cards. A, B, C, 1, 2, 3, 4. And I shuffle them random. What is the probability that letters are in order? And numbers are in order. That is, if I do A, 1, 2, B, C, 3, 4, that's valid because the numbers are in order, not consecutive, but they're in order, and the letters are also in order, not consecutive. So what's the chance to leave, if I shuffle it at random, What's the chance to have the letters in order and the numbers in order? How do I think about this problem? What is my space? Yes. 7 factorial. It's all permutations, right? And my event is all permutation that preserves order. Permutations that preserve letter and number order. Is this space convenient for counting? Is every outcome in it equally likely? What's an outcome here? An outcome is a permutation. Is all permutations equally likely? Because it says shuffle at random. And that means any possible order of those 7 cards is equally likely. So what's the probability of one outcome?
1 out of 7 factorial.
1 over 7 factorial. So I need to count, if this is a space that's uniform, this question comes down to counting the permutations that have this property. So it's a count of permutation that are valid divided by 7 factorial. The question is how many permutations have the letters and the numbers in order? How do we do that? Remember those problems with the songs by Lady Gaga in the online homework? That's the kind of flavor that's in here. How many permutations? How many permutations will have? What are your choices when you try to generate all the valid permutations? Or how can somebody help me think about this problem somehow? Yes.
So choose 3 slots for letters.
Right, so he's thinking here's the permutation, right? 7 things. And he's saying, you say choose 3 spots for letters. Letters. So for example, this spot, and this spot. Can I choose anything else?
Do you need, like, are there other available spots for letters?
Am I done? Or is that determines the permutation now? Why? The letters have to go in the order A, B, C, and the remaining ones are the numbers, which have to go in the order 1, 2, 3, 4. So I'm done. So how many permutations can I get? 7 choose 3 divided by 7 factorial. Okay, last problem. Once we establish a space that's uniform, it's down to a counting problem. But make sure you don't have a space that's not uniform, because then counting doesn't work. I have a coin. It's fair, so probability of a head is 1/2. Probability of a tail when I throw it is 1/2. I flip n times, because they're independent. What is the probability to have exactly k heads? So if I flip it n times, I'm looking at those flips. 1, 2, 3, up to n. And I'm going to see something like head, tail, tail, head, head, tail, tail, so on and so forth, right? What is the chance to see exactly k heads? So I have a coin. I flip it 100 times. I record. It's with repetition, right? Every time, I mean, the second flip has exactly the same chance of the outcome as the first flip and the third flip. They're independent flips. What's the chance to seeing exactly 35 heads? out of 100 flips. What's the chance to seeing exactly this sequence in order? So that's different, that's a different question, right? Exactly this sequence in order is, what's the probability of this guy? 1/2. What about this? 1/2. What about this? 1/2. Up to 1/2. So the probability of this particular sequence is gotta be 1/2 to the n. So what am I supposed to count now? Every single sequence of n trials, that particular exact sequence in that order will be 1/2 to the n. What sequences matter to me? The one that have? How many sequences of n have k heads somewhere in there? N choose k. So I have n choose k sequences of k heads. So what's going to be the probability of seeing exactly that? N choose k times
1/2.
What if I tell you this is not a uniform coin? The chance of a head is 1/3. The chance of a tail is 2/3. This is not 1/2 anymore, right? What's the chance of a head? 1/3, 2/3, 2/3, 1/3, 1/3, 2/3, 2/3. I still have n choose k sequences of k heads. What is the probability of such a sequence with k heads?
Would it be 1/3?
How many 1/3s I'm going to have in there?
Would it be 1/3 to the k times 2/3 to the n minus k?
And what's the total chance of probability? That's for one sequence. But how many sequences I have with k heads?
N choose k.
So it's n choose k, 1/3 to the k, 2/3 to n minus k. Does this sound familiar?
Yeah.
What is it? This is a binomial theorem. This coin that has a particular bias, this is a biased coin because it's not fair. Anytime you see a coin flip many times, immediately try to remember the binomial theorem because that's the one that's in there for counting. We'll pick up on Tuesday. Cubes, if you didn't pick up your cube, here it is. Oh, maybe the order. I think the difference is one is in order, one is out. This is in order because the first red will be the second red. But the out of order, I that's the right If you look at a physical model, say if I take a card like in a diamond, I have 51 cards remaining. Yeah, that's okay. I think that's okay. You should think about it like I said. If you have it in your head settled, it's dangerous to unsettle you for 2 weeks because you get confused. Eventually, you go towards mathematics. You need a little not all problems can be. Cards can. I would, for now, if you can, try to have this space in your head. What are my outcomes? What is it? An outcome? One kind. And then I have the uniform one. If the uniform comes out,
Shut down my microphone. You have the two problems, so we have vertical, and we
Yeah, if you do it, you have to figure it out.
have